In this lecture, we're going to do another little demo on a time series, but this time with a much more complicated signal. It's still going to be a synthetic signal, meaning we can understand its behavior because we know the mathematical formula that represents it. But as you'll see, just one small change will make this task much harder for both the autoregressive linear model and the RNN. This lecture is going to walk you through a prepared Colab notebook, although a very good exercise, which I always recommend, is once you know how this is done, to try and recreate it yourself with as few references as possible. As usual, you can look at the title of the notebook to determine what notebook we are currently looking at. Okay, so after the imports, we create the time series. As you can see, it looks very similar to what we had previously, but with one crucial difference. This is that we are squaring the input argument into the sine function. Because we square the input argument, this means that the frequency, and hence also the period of the wave, changes over time. So let's plot the time series. And we see exactly that. In some parts, the wave goes up and down very fast, and in other parts, it slows down. In the next block, we build our data set. Now, because of my rule, all data is the same, nothing about this changes, so we don't need to explain this again. Next, we're going to build an autoregressive linear model. You've all seen this before, so I'm not going to explain it again. Okay, here's our loss and optimizer. Here's our train test split. Here's our training function. And here is running the training function. So let's see how this performs. So it looks like the loss is pretty high, about 0.5, 0.6. This is much higher than what we had before with the normal sine wave. Next, we're going to plot the loss per iteration. Alright, so this does not look very good. In fact, it looks like the test loss does not decrease at all. The train loss appears to decrease, which is a sign that all the model is doing is overfitting without actually matching the underlying pattern. So for our predictions, let's start by doing a one-step forecast. As a side note, you'll see that I've taken a little shortcut here. If all you want to do is a one-step forecast, we've already built our input data for that. All we need to do is call the model and pass in x_test. Remember that the first half of x is our train set, and the second half of x is our test set. Alright, so let's plot the results. So as you can see, it does not do very well. It doesn't even get the values in the right range. Knowing this, we can deduce that the multi-step forecast is going to be even worse. Again, since we've already gone through this code, I'm not going to explain it again. So let's run this and see what we get. As you can see, our suspicions are correct. The linear model does a terrible forecast. So we're going to switch notebooks now. Now we're looking at PyTorch nonlinear sequence simple RNN. So in this new notebook, we're going to try an RNN model. We're going to start with a simple RNN and then move on to an LSTM later. The only different thing we need to do here is reshape our data so that it's three-dimensional, n by t by d. Then we create our RNN, fit it, and look at the results. So we're going to set the device, define our simple RNN. You've seen this before. instantiate the model, create the loss and optimizer, make the inputs and targets, do our training, move to the GPU, do full gradient descent, all right, so you can see that our loss is now better than the linear model. Now this is a good lesson. For a simple time series like a sine wave with no noise, a linear model is perfect. An RNN does worse, at least with default parameters. It has too much flexibility. But now we have a signal that is much more difficult, a signal that a linear model can't solve at all. In this case, the RNN does better because it actually has the flexibility to match the signal. Next, let's plot the loss per iteration. All right, so that seems reasonable. Next, we're going to do a one-step forecast. So as you can see, this does a much better job. It looks like it can match the frequency in most places, even when the signal slows down significantly in the second half. This is despite the fact that the model never saw such a low frequency in the training set. The values are also approximately in the right range. Now let's go to the multi-step forecast. So as you can see, this doesn't look that good, but at least at the beginning, the model appears to capture the frequency quite well. It doesn't know that in the second half, the signal slows down, so it kind of makes sense that the model isn't able to predict that. Also, it does a much better job than the linear model at getting the right range of values. Finally, let's go to our next script where we use an LSTM instead of a simple RNN. So I'm going to run the imports, make the series, plot the series, build the dataset, set the device, define our RNN. So this uses an LSTM. Instantiate the model, create the loss and optimizer, make the train set and test set, create the training function, move data to the GPU, train the model. All right, so the loss values are still small. That's good. All right, so the loss goes down pretty smoothly, and we get a slightly better loss than the simple RNN. Let's look at the one-step forecast. All right, so I feel like the one-step forecast looks a tiny bit better. And if we go to the multi-step forecast, I don't think there is any appreciable difference in the multi-step forecast. So essentially, this is pretty much the same as the simple RNN. Now, why might this be? Well, don't make the mistake of thinking that LSTMs are more popular, and because they are more popular, it's probably because they are more powerful, and therefore LSTMs are better and they can do anything. LSTMs are better than RNNs at finding long-term dependencies. But this doesn't mean that LSTMs are simply better at everything. It doesn't mean that LSTMs are magic. Now, although LSTMs are good at finding long-term dependencies, it's important to realize that this fact doesn't hold true for arbitrarily long-term dependencies. There is a point where even LSTMs forget. Of course, that point is further than the simple RNN, but it exists nonetheless. So avoid absolute generalizations, first of all. And second, note that this dataset doesn't really have any long-term dependencies. at least for the time span of the dataset as it exists right now, data from very far in the past isn't really going to help predict future values. So in fact, it makes sense that there's no real advantage to using LSTMs for this problem.